so far we've talked about bijections which preserve the structure of a group, that preserve the multiplication operation. But I'm going to introduce a sort of generalization of this idea, so things called homomorphisms. So for instance, the determinant map from, say, GLN R to R star, which, again, per our previous notation, is the non-zero elements of R with multiplication as the group operation. Well, it's certainly a well-defined map, and we know that the determinant of AB is the determinant of A times the determinant of B by basic linear algebra. Is this thing an isomorphism? No. What's an easy way of seeing that it's not an isomorphism? One of them being, for instance, that this is abelian and this is not. So certainly det is not one-to-one. And in fact, there can't be any isomorphism between GLNR and R star. But nonetheless, it does preserve the group structure. There can be bijections. In fact, these two have the same cardinality, but you can never show that they have the same group structure. So the question was, could there be bijections? Yes, there certainly can be bijections, but they'll never be isomorphic as groups. Yeah, the formalization of this idea, where you have some sort of map and it preserves the group structure, but we don't make any sort of assumption that the thing is bijective. That's this idea of homomorphism. So our maps F between groups such that f of x times y is f of x times f of y. And so every isomorphism is a homomorphism. Suppose I have a pair of groups, G1, G2. Is there necessarily a homomorphism between them? So there's always a trivial homomorphism between any two groups. Trivial homomorphism so between G1, G2. And that's defined by just taking f of x to the identity element of G2. That certainly preserves the group structure because f of x times y, well, that's automatically E, and that's automatically the same thing as f of x times f of y because both of those are E. We talked about S3 as if it were a subset of Sn. Is that a bit problematic? I mean, insofar as something that's a function from the set 1, 2, 3 to itself isn't really a function from the set 1, 2, 3, dot, 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 n to itself. But we thought of the elements in S3 as if they were in Sn for n greater than or equal to 3. Well, so this gives us another example of a homomorphism. What we really were doing is we were taking things in S3 and we were giving them just the identity structure on 4 dot, 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 n. And the whole point was that because of our sort of intuition about these things, we know that the same group structure that was on S3 is going to be preserved onto whatever the image of this map was. So we had S3 to Sn for n greater or equal to 3. Well, what we did is we took some permutation rho in S3 and we redefined the thing. So rho 1, rho 2, rho 3, according to how they're given. And then rho k be just k for k equals 4 dot, 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 n. So this is certainly a new permutation. This is something in Sn. But it's easy to verify that this thing preserves the group structure because all we're really doing is we're just saying leave the thing to be the identity on 4 through n and do the things on 1, 2, 3 as before. This thing is injective. So far, only isomorphisms we've seen, we've only seen injective homomorphisms in the case of isomorphisms. But here's an example of an injective homomorphism which is not an isomorphism. Here's another example. I'm going to take the map F from the integers to the symmetric group on 2 letters, and I'm going to define it as follows. I'm going to take all of the even numbers to the identity element, and I'm going to take all of the odd numbers to the transposition in S2 that we introduced on Wednesday or Monday. And it's pretty easy to see that this preserves the group structure, because if I add evens to evens, then I get evens. If I add odds to odds, I get odds. And if I add evens to odds or odds to evens, then I get odds. So this thing is certainly a homomorphism. It's well defined. And it's another sort of example of a homomorphism. And it's going to be a sort of nice replicated example.